Das ist zu weit.
Hello, everyone. Today, we hear from a Future Earth Coast organized webinar delivered by Professor Dieter Kelletat, a pioneer in tsunami, boulder and paleo tsunami research. And his presentation is titled Coastal Boulder Deposit Research, an invitation to a virtual field trip and open discussion. Please be aware that this webinar will be recorded. And firstly, I would like to acknowledge the traditional owners of the country that I'm living and working on, and extend that to wherever you listen to that webinar. Dieter, I hand over to you.
Thank you, Anja. Well, ladies and gentlemen, dear colleagues, welcome to our short presentation on some aspects of coastal sciences under the headline Coastal Boulder Deposit Research, an invitation to a virtual field trip, and if you like, to an open discussion. In 2007, Dawson and Stewart expected that boulder complexes deposited by tsunami may represent the most promising area of scientific inquiry. However, many deficits in coastal boulder research still exist because theoretical approaches more and more replace the detection of facts from nature's reality, which is our business. This concerns the main question of processes responsible, storms or tsunamis, as well as details like relation of boulder forms and transport energy, or the question of friction during transport, mechanics of imbrication, evaluation of signatures in fine and coarse sediments, in contrast in respect to any transport conditions, or the intensity of weathering as indicator of post-depositional processes, and many other environmental factors like bathymetry, history of sea level exposure, and all, of course, also history of the deposits themselves. In 2020, Watanabe et al. Demand that calculations and models remain theoretical tests based on numerous assumptions related to simplifications of actual phenomena. A very critical point. My impression is calculations and models rarely include past conditions hidden in deposits. Next, please. Here are some introductory remarks to avoid misunderstandings on what we are talking about. We mean geoscientific research means open-minded dialogues with landscapes and field signatures from past times. And when we talk about boulders, we mean remarkable or erratic clasts, no matter of their size, in coastal landscapes, even in sheltered positions where they may be small, less than 1 meter, but may be enigmatic, remarkable, erratic, anyway. And when we talk about moving of these clasts, that means significant dislocation against gravity, excluding movement supported by gravity or movement at the same place, some wiggling or whatsoever. Next, please. As our key question is, which forces have been able to dislocate masses onshore from the littoral or from the sea or land and upwards? These here presented moved coastal boulders are out of concern in the discussion on storm waves or tsunami waves. The upper ones show ongoing cliff collapse, and the right image, which is with a boulder of about 800 tons, is just a part of that, but from a former phase of this collapse and now separated from the active collapsing cliff. is the same side. And the lower one shows the same boulder from two a little bit different aspects, but you will easily understand how this works. This is a boulder which was published as an example to show the world how climate change will enhance the dynamics of waves and will come over to us and ashore. But as we can see, the left image is from 2007 and the right one from 2015. In between, there have been the strongest storms ever on record and in memory of the locals along the Irish West Coast or in the Eastern Atlantic. There were 6 hurricane force storms, wind forces up to 250 kilometers and so on. You see, this boulder just wiggled a little bit, but its relation to its place can be identified by the contours of the pools, the water pools, and the green algae in it. So it is nearly at the same place. The left one, in meantime, and by these very strong storms, lost an upper platey part. So it lost maybe 2 tons of its 600 tons of weight. Next, please. To establish a close approximation to nature's reality and history by strong chains of arguments, we need to collect as many different, as many different field evidences as possible. Not a very high number of evidences. Let's say we measure and calculate thousands of boulders at the same place. That is not the point. The point is different field evidence from different sites and different types, different ages and so on. But nevertheless, in publications, important facts in this relation often are missing. The origin of boulder, or what is the petrography, their transport distances, vertical and horizontal, or geomorphologies in the macro and micro scale, boulder formations, the weathering, as I mentioned before, or history of deposition and exposure, nearshore bathymetry, or, very important, the history of sea level when the boulders have been moved. So take as an example for our excursion area, which is a Galway region with the Aran Islands in Western Ireland. There in this region, Galway region, they experienced a drowning of 5 meters over the past 5,000 years. While Ireland's north coast, just 300 kilometers apart, had an emergence from the sea of 2.5 meters by glacial isostasy, resulting in about 7 meter altitudinal difference in boulder dislocation if we compare a Galway site with a North Island coast site. And if we don't have the idea on sea level history and age of the deposits, we try to compare. It is, yeah, let's say we come out to nonsense. We will not find a reason, a good base for discussion. Our presentation now only picks up a few examples from the multitude of morphologic and sedimentologic field documents very shortly. So the next figure, please, shows a collection of boulder formations. They may appear in very different kinds in the landscape. The upper left is an example from our research on the western Australian islands of the Abrolhos, coarse coral rubble, nicely ordered into boulder ridges or beach ridges. We dated them over about 1,500 years, which means that because of the high number of these ridges, every 30 years we may have an event which was able to leave these signatures. Upper left is a 700 meter wide coral reef platform in southern Japan. And you see a clear envelope. The darker part to landward is a collection of very large boulders from historical tsunamis, like the Meiwa tsunami from 1771, and the seaward part, the lighter part, shows some strewn individual boulders from the many typhoons which are active in that area. The picture in the center shows a kind of boulder cluster or boulder line, a person, a scale at the extreme right side. And you can see that the boulders all have a dark upper part and may have light colors all around. The upper part shows a long time exposure and the karstification, because this is coral rubble and reef rock, and eolianite, all carbonate rocks. And therefore we know they are immobile over the time of this intense karstification. And we were able to date this deposit to a tsunami about 3,000 years ago. And we can say that because the position here and another one a few hundred kilometers apart on Cat Island and Long Island, the same data, are in the full track of high category hurricanes, category 4 and 5. And so the modern hurricanes hit these areas without overturning or mixing up these boulders. On the lower line, we have erratic boulders from Bonaire in a vegetated landscape. So erratic, enigmatic, why there are these boulders in the strange landscape. Vegetation is at least several hundred years old. And in the center, we see a contrast of the same material compared to the abrolhos in the left upper part. Here as a rampart, as they say in the Southern Caribbean, kilometers long originally before mining of these archives, and about 2 meters thick and 100 to 300 meters wide to inland. The dating with several hundred data and then shows a lot of inversions, data and age inversions. And the right one is the largest boulder from Tonga, published 35 years ago. The first time also erratic, but this is a Holocene deposit. The age is still open so far as I know. Next, please. Let us now visit the Galway-Arran region. It's the central west coast of Ireland. What will we do there, or what have we done there over the years? To collect field evidence and data by observing, comparing, sampling, and dating. So far we have 84 numerical ages. To tell a history of sediment deposition over the last millennia, for comparisons with coastal landscapes and deposits worldwide, as a contribution to the state of the art in our science. The study area of Galway and the Aran Islands is dominated by sedimentary rocks, which allow to collect more field data compared to other types of rocks, like massive magmatic rocks and so on. Especially limestones preserve a lot of signatures from the geomorphologic history. Fortunately, many carbonate or limestone rocks exist in rocky shorelines around the world. Because of its extension, variety in relief, exposure and bathymetry, richness in boulder formations, and histories of sea level and deposition, the Galway and Arran region is one of the best natural test sites to uncover the process histories of Holocene coastal boulder deposits in the world. Next, please. If we will compare our data at any field site we are working with others, we first should get an impression of all of the environment we are working in. Under the headline, the stronger an event, the larger the area which is affected by this event. That means if we have the impression there have been strong events because we have huge boulders or a large amount of material, high onshore and high inland, or in thick packages and so on, or in many different formations, we are aware this must be an extreme event, and extreme events affect large areas. And that is what we've done here in the Galway an Aran area which has coastlines of more than 200 kilometers. The northern one is not so very interesting. It is from granite and shows a glacial landscape with some remnants of basalt moraines and rocky outcrops. But the southern one, including all Aran Islands, is made from the same type of rock, from Carboniferous limestone, a very hard, very resistant, well-bedded limestone. So the points which are indicated there show localities and the methods for the reconstruction of the sea level for mid-Holocene times, about 5,000 to 6,000 years BP. And all these came to the result that the sea level at that time was at -5 meters. The number one is on Inisheer Island and is taken from Holmes and Shetler from the sediments in a karst lake, the bottom sediments in the karst lake, reconstructed from micropaleontology. Numbers 2A and B, 2A on Inishmore Island, 2B near Doolin on the mainland, have the same aspects. There is a soil without any marine grains or any marine particles in it, so a totally terrestrial soil with charcoal drowning today in the level of surf beat during normal storms. And we dated the charcoal there on both sides with 6,300. Number 3 is a now drowned depot of sand, which was the depot for outflows for the Fanor dunes. Fanor is at the red dot, number 3, on land, now inactive dunes and now cut by storms or by waves, by erosion in the cliff, because the sand depot, evidently from meltwater during late glacial times, is now hidden, drowned, and cut from these deposits. Number 4, at the Connemara coast, is a Bronze Age tomb from about 3,500 years old. And it is sitting now in the modern reach of surf beat, and it is lower than the crest of the normal, even summer active beach ridge. So there is also in older times a signature in this for lower sea level. And the best site is number 5. It's a drowned freshwater peat in which birch and oak stems can be found, and a Neolithic canoe, which is buried there and now in a museum. It's 5,000 years old. And this freshwater peat had its base where today the mean low water level is, which is 5 meters below the mean high water. So sea level must be significantly and at least 5 meters lower in the middle Holocene. Next, please. The landscape we are looking for, the coastal landscape, is built and formed on a glacial landscape. Last glacial maximum ice left these areas about 15,000 years BP. And since then, everything is fully exposed. You see the nice glacial forming and sculpturing, these fine soft surfaces. Left Black Head is inside Galway Bay along its southeast coast, and it's just drowning under modern sea level. The right part is more exposed at the Inishman's west coast. This is the middle island of the Aran Islands, and you see that these down curving of glacial morphology is cut by cliff processes. The last glacial maximum ice border at that time, 15,000, maybe 16,000 BP, was at least 100 kilometers west of Ireland. These are new data, along a carving front detected by numerous iceberg scores on the shelf. So our forefathers living in Spain or in southern France or in southernmost Cornwall looked to floating icebergs like we today have similar aspects in Greenland. Now, next please. Archaeology, rich in Ireland, of course, allows to calculate intensities of gasification or cliff retreat. We can use on English more alone, at least these two sites. Left is the Bronze Age fort Dan Aung Gaza. It is dated to 3100. It is surrounded by a chevaux de frise, a belt of sharp rocks hammered in fissures of the bedrock and upright standing to break the attack of horsemen enemies to attack the fort. And the other fort on the right side is an Iron Age promontory fort. On this small promontory, dated between 2000 and 2500 BP, the Black Fort. And this is interesting because it was used by Williams in 2004 to calculate on cliff retreat. This is a special point of discussion because there is a sharp difference or a wide difference between his data and our data today. Next, please. Cliffs and rock platforms are the dominant geomorphologic features in the Galway Arran region, in particular in the extremely opposed ones. And cliffs in the local limestone are extraordinarily stable. We see on the left side, the site of this Bronze Age Dan Aung Gaza fort at top, at a 70-meter high vertical cliff. So there was no cliff retreat over at least 3,000 years at this place. But if shales or siltstones are incorporated into the limestone, you can identify them in the left image, these dark, very fine bands rising a little bit to the right. And at the base, one which shows a very wide notch, then surf beat wash out the siltstones and shales, and we get huge overhangs of cliffs. The right example, the cliff is 20 meter high and the overhanging is more than 25 meter. But as you may imagine, this is not a long living morphologic element, and there will come a huge collapse and huge amount of deposits in any size. Next, please. Those processes of collapsing of rock steps or rocky cliffs undermined are described in the literature that they have sediments at the landward side of the platforms, large boulders or large fragments, and at the foot of the next step or next cliff. This is not the same on the Aran Islands, because the lower and intermediate rock platforms in front of the higher cliff are totally bare of any sediments. And the sediments and the boulders and ridges and boulder belts appear in cliff top platform, though on the highermost levels. Next, please. Here you see the mapping in yellow of the extension of the boulder belt or boulder ridges, so boulder formations in any form, boulder clusters, and so on, all around the Aran Islands and along the southeast coast of Galway Bay. And what is important for us or for everybody, they are not only formed along the most exposed sides to the open Atlantic, but also to the sheltered sides of the islands in direction to the Galway and in the Galway Bay. And we should know that the water depth in Galway Bay is mostly less than 30 meters. Just the entrances, the two large ones in north and south and the two small ones in between the islands, have water depths of 50 meters, and then water depth goes down to 30 meters on approaching the mainland coast to the southeast. goes to 20 meter and 10 meter and less. And today, every wave which comes in from the open ocean during some storms with a wave height of 5 meter or more lose energy because the water is too shallow for these waves to cross the bay and meet the southeast coast of Galway Bay. And if we now know that sea level was 5 meter lower a few thousand years ago, then this situation was more shallow for waves, and wave energy was much less. But in these yellowly these designed parts of coarse deposits, we have a lot of data which are around 4,000, 500, 1,000, 6,000 pp. So from a time of low sea level, which evidently lower wave energy than today. Next, please. Another point of discussion is the relation of boulder forms, boulder mass, but also boulder forms, and the energy need to move them. And as you see on the upper side, a platy boulder or a flat boulder has a very small cross section compared to a round or square formed boulder, and has or may have a very large base. That means a small area where a wave will strongly hit the boulder, but a large area on which the boulder has contact with bedrock. That means high friction. But we found at many places that the movement of platy boulders from the bedrock can be found at many places in many situations. The upper pictures are from Hurricane Ivan in 2004 on Bonaire Island in the southern Caribbean. On the left, a platy boulder which is dislocated now. It is not the right one on the right picture. That is another one overturned. And in the lower picture, we see a large platy boulders there in the imbrication train. This is from Lisbon tsunami 1755 and the coast of Morocco south of Rabat. The largest boulder is 9 meters long. The weights go between 50 and 100 tons, and the arrows indicate which of these boulders are overturned and which are still in more or less normal position. The overturning it is identified by rock pools made from bioerosion near 10 meters deeper along the sea level, and which now look to the bedrock, so to the lower side of the boulder. So we certainly and for sure can identify the former position of the boulder and its way. Next, please. Here we have an example from the near-time inspection after these hurricane force storms, the two clusters of 3 hurricanes, end of 2013 and early in 2014. The source area in February 2014 is in the front, and along a more than 12 meter long edge, a plate of more than 50 square meters was lifted vertically. One of these parts of this lifted plate was deposited a few meters apart, where now the yellow arrow points down and there is a little bit yellow surface. In the small insert, you see this boulder is more than 7 meters long, and it was lifted vertically, moved aside without ground touching, and then settled down very smoothly and just got one crack or one fracture in the middle. And from this fracture and separation into 2 parts with half of the mass, in 2015, in the next winter storms, one of these parts was moved to the cliff, where we find the number 2015, and the other one is lost into the sea. And from these 5 boulders, which have been platyboulders which have been displaced. 3 are overturned in these processes, and they had barely no friction with the ground. Next, please. And a next enigmatic thing is imbrication. Imbrication of very large boulders. The best imbrication can be found along the southeast Galway Bay. You see there's some examples here. There are more with imbrication trains, very long ones. And here boulders up to 50 tons are incorporated. And as you may also see, these carbonate platy rocks are partly strongly weathered, so they lost their sharp edges. They lie there over a long time. They built a very strong protection against any wave attack to inland, no matter whether sea level rises or not. But it has risen and it attacks there, but this protection is strong enough, and it's very difficult to destroy by those forces which once made it. The question is it true that imbrications in this amount and this perfection have never been found in tsunami processes? We doubt this, and we published it. This in particularly concerning the 2002 Tohoku tsunami. The reason why someone may come to the conclusion that tsunamis cannot make good imbrication maybe we have 2 less studies on coarse deposits during recent tsunamis. Everybody looks for the fine sediments and their characteristic deposition. Next, please. The boulder origin can be seen by these 3 light-colored boulders on old ones after these hurricane storms. They derive from the littoral, seen by the coating, the white coating from calcareous algae and barnacles. And these coatings and color will disappear over time, over many years, and then it's difficult to say from where they came. But they have been lifted or moved by saltation, because we do not find from their origin to their resting place any mark on the ground. But we find those marks in the form of striations on the bedrock at many places, but they mostly are soft and interrupted, as you see on the right below on this photograph. So the contact of even ton heavy or boulders of many tons in mass mostly is smooth, and we rarely see deep scratches which remain there as signature. And these light-colored from limestone boulder on limestone bedrock, light-colored signatures disappear within months or over a few years, and then we have no documents any longer for a kind of friction, intensity of friction, or even way of movement. Next, please. If you look a little bit closer, even in particular in limestone areas, on bedrock and on limestone boulders, we find a lot of bioerosional signatures, which allow to identify exactly the place of origin of these boulders. In the left section, upper left, you see home places of sea urchins. They normally live in the lower tidal or in the subtidal, upper subtidal. Right is one home place of a limpet, a patella, a limpet as a mark, and they live for decades or centuries. In the middle, with the finger, the two aspects of the same thing, boring of the sponge Cliona, boring in limestone, and the lower pair is from boring of bivalves, in this case Hiatella arctica, which is very widespread in the area of Ireland and to the Shetlands and further north. The borings are a few centimeters deep and sometimes just a centimeter across. On the right, we find from the level at the upper tidal, the upper one, rock pools with a flat bottom and sharp little notching, covered by totally covered by barnacles, which is sea level. And the lower picture on the lower right, these are rock pools grasped and formed by littorines, by hundreds and thousands of littorines, flat bottom, a rounding notch. Diameters here are 1 to 2 meters, and measurements directly with bioerosion meters over times. They have identified that this kind of bioerosion from all these organisms comes to about 1 millimeter per year. Let us remember this figure. Next, please. On land, we may find clusters of boulders and ask how long have they been at the place, and we can try to estimate relative ages of their emplacement and maybe of their immobility. This is the same boulder cluster on Inishmaan with a picture from land on left. There you see the cover of lichens, these yellow-orange lichens, and it looks for longer immobility, which is right. Time span with many decades, maybe 100 or 200 years. The right side shows the same boulder group from the seaward side, so it looks fresher. No or nearly no lichens, but it shows these rock pools with the flat bottom and notching around, now dislocated or tilted in these boulders, and they have strong vertical outrunning channels of dissolution in the limestone in an environment of rainwater. And in this environment, the dissolution of limestone is very, very slowly, 30 to 50 times slower than that of bioerosion. That means to form 1 millimeter or to dissolve 1 millimeter of rock needs 30 to 50 years. And the dimensions of these outflow channels from dissolution give the idea that this rock cluster is in that form without any change, although in strong surf beat a very strong winter storm over more than 1,000 years, maybe more than 2,000 years. Next, please. For the calculation of the intensity, we can take or can test the dimensions from natural and from archaeological sites. The left one above shows the karst tables, 2 karst tables where granite boulders from Connemara lie on limestone bedrock. And the table, the fundament, has elevations of 25 to 35 centimeters on average in about 60 to 80 samples we have seen in the landscape. And as we remember that the ice left the area about 15,000 years ago, we come to an intensity of dissolution or in this case, protection from the dissolution of the surrounding area of 0.02 to 0.03 millimeters per year. When we go to the Chevaux de Frise, these upright standing rock labs around Don Arangaza, dated by archaeologists to 2,800 years, we find just 1 or 2, a maximum 3 centimeters of dissolution on the upper elevations, like that on the left boulder on the left side. And this means 2,000, 3,000 years or a little bit more stable position. And these little basins or on the right boulder, there are little bits of Rillenkarren, so small bends or carved in the rock. So next, please, next one. Around, next one, please, yes. Around the boulder deposits, we find rare and tiny deposits and archives in smaller grain size. Not very small, mostly a little bit mixed. And they are chaotic and unsorted, but in reach of every winter storm. So it's very unusual in storm wave dominated environments that sediments left there over a very long time are looking like this. The left one, the scale in it is 0.5 meter altogether. Has two sheets. The lower one is a loamy silt with angular clasts in it. And the upper unit is coarse sand and shell with stones. The central one is 1 meter deep, chaotic coarse sand and cobbles, well-rounded cobbles from a former beach, here mixed with sand, and with one irregular marked patch is a mud ball, mixed with mud balls, and within these chaotic deposit are limpet shells, some ring-like, and these ring-like limpets can't be transported many times, otherwise they have been broken in little pieces. That upper left, which the largest oval marker, has been dated to 2,700 years. On the south coast of Inishir, we find another mixed and unusual and unsorted deposit. It is a mixture from sand and shell with rounded and angular stones in it, 1.20 meter deep, and on top some younger boulders from strong storms or tsunamis. We could identify that. Next, please. A very tiny archive here, which is just a little bit more than 0.5 meter thick and 1 meter wide. It shows at least 3 different layers with basal unconformities, but more significant is the fining upward grading in each sheet, from coarse sand with a little bit petals and shell to finer sand. And then the next. So in 3 units. And the dating of them show these are not deposits from one event and 3 waves, as it might be possible in a tsunami, but the times are too much apart. Though there are 3 different events, and this kind of sediments with fining upwards and in series upwards at all are significant for finer tsunami deposits. That is the state of the art. Next, please. In very rarely we find sediment deposits and archives which show better bedding and forming sheet for sheet, and which give the impression that this is an ordered sediment, the oldest data below and going younger and to the upper part. And this is also the case in connection with the Boulder Ridge on Inishmaan Island. So in a rather high exposure. And you see we have 6 data. The lower most of the left and the highest of the right one have the similar age, and so we have here altogether 9 levels on 9 deposits with topsoil. This is a little bit grayish and darker, and subsoil which is brownish like a B horizon. And the time gaps in between this sequence of deposits related to the Boulder Ridge spans more than 4,500 years, and the time gaps in between may be over 400 to over 800 years. Next, please. Now we come to the chapter of what happened by the hurricane force storms on older deposits. What we know by our dating, that the old and wide extended deposits in clifftop positions span many thousands of years of depositional history. And we are rather sure that the hurricane storms from 2013 to 2014 have been the strongest ones in living memory, and surely on registration with the category 3 and 4 hurricane forces. Within less than 3 months, 6 of them. So this is an example from the south coast of Inisheer. All of the relief you see is lower than 10 meters above mean high water, so it's a low area. The black frames mark activation along these old deposits, so in very light colors, activated by the storms, mostly in a kind of erosion, so washed back, material is washed back into the sea. And the white frames mark boulder clusters remaining mostly immobile. Maybe the one or the other has been overturned or moved a little bit and has no white dot in these dark clusters. Next, please. We have a look on this area where this comes from. This is Inisheer, south coast, and the clusters we have seen just in the image before is this area here. You see individual dark clusters. You see an enrichment of dark, large boulders to seaward of this main boulder ridge. And the insert picture shows you the landward slope of these boulder deposits, which is similar on all the Aran Islands, which is chaotic. They are large boulders, some very large, 5 meters long or something like that, and they mix together and they have no order, nothing at all, and they are inactive over a very long time. So the image overall gives the impression that an older deposit built over a long time is in younger times with rising sea levels, with 5 meter rising sea level over 5,000 years, is in a kind of erosion and with an enrichment of the largest, which left longest in that place. Next, please. Next, please. So here we see a similar environment, but on Inishmaan Island, which is higher, has a higher relief, and we can follow these deposits to higher elevations. You see left down in the inset the frame, the small frame, which is given in the large picture. The crest of the main boulder ridge is marked by a red line, and the figures give the crest elevation above mean high water. So from the right side, from 6 to 7 meter, then over the south or southeast coast, 8, 9, 11 meter and higher and higher and higher. And the highest one here in this image is 35 meter above mean high water. In fact, the highest is 37. And the color, the change of color by the hurricane storms can clearly be identified in the lowermost parts on the right, on the southern section, where the hurricanes overwashed the whole belt. So if they are lower than 10 meter in height, they have been washed over and the belt is activated on the seaward and landward slopes and on the crest. Then with more distance from the shoreline, from the modern shoreline, and a little bit higher, the activation is restricted more to the seaward slope, a little bit more higher, there is a punctual activation at the seaward slope, not a general one. And when we go higher in the landscape, there is no activation at all in elevations more than 20 meters above sea level, and it ends at 37 above sea level. So we see a strict envelope in distance to land and in elevation made by these hurricane forces, the strongest in living memory at the time of the highest sea level of the Holocene. Next, please. Now we come to the last morphological section, looking on the formations and their hints to transport processes. We know overwash features in sandy environments by storms and breaches in beach ridges and overwash into lagoons and so on. But in coarse deposits or very coarse and boulder deposits, they are rare or they look just different. These is an image from the western end of Inishmore. On the left side up there, you see two arrows. The northern arrow coming from the north-northwest shows a tongue, a boulder tongue, which is shown even in the right upper image. The tongue is over 140 meters long. It is 6 meters thick. This deposit has a very sharp outer contours and steep front. And it is washed in as a deposit. It was a depot of pebbles, of well-rounded pebbles in the tidal and subtidal area in a very, very short moment, like in high mountains, we see rock and rubble rundowns after a very heavy rain, when all the pores are filled by water and friction is diminished. And the other washover feature is made by irregular angular and a little bit rounded boulders. Size goes partly over 10 tons coming from the south, and the way to inland is 170 meters. The weight is more than 45,000 tons of pure rock or without pores, calculated, moved in a short moment. But we think that these white, dark and coarse overwash feature has several generations in it, whereas the other one is only from one event. Next, please. Here along the mainland coast, near Black Head, 22 kilometers inside Galway Bay, on the left side, we see two of boulder tongues. The lower one has contact with the surf and with the sea level, but a sharp landward slope, and the other one is free in a kind of gap behind the oceanwards imbrication rift, and it is more than 100 meters long, has sharp contours, and it is moved, both are moved from forces coming from the south and near coast parallel, and tongues like this or deposits like these with sharp and steep outer contours, and then in a suddenly stop, have been moved in a very, very short moment, and no more forces have transformed these general or the first forms definitely. In the lower photograph from 2014 CE, I marked the limit of lighter colors on top of this boulder tongue, here seen from the land to the sea. This is a little bit activation from the hurricane waves. They washed on this without changing its form, but it didn't reach the landward slope totally. So we have these boulder tongues, never described before 2015, before our first publication on it. And I wonder if all these deposits, as several publications say, are all storm wave effects, that we don't have more knowledge on these forms in boulder deposits along the coastlines of the world. Next, please. There we can another formation, which also has been unknown until the last years. Here we see the uppermost, the highermost section of the boulder belt or boulder ridge of Inishmaan Island from the very exposed western coast on a length in the red color, marked in the red color, on a length of 750 meters, the upper section from 17 meters above mean high water in the right to 37 meters above mean high water to the left. And the left-hand part, the highest one, is shown by the insert on a vertical 30-meter cliff. There are these ridges, they're running crossway to the main direction or even perpendicular to the cliff line or to the coastline or to the main direction of the boulder belt. And they are not formed one after the other, because in this case, the highest one on the left and highest part must be the oldest, and then all younger and younger and younger. But they have been formed in one strong event. The question is, what we see, is this the result of this formation in one very strong event, or have there been a belt of boulders and coarse pebbles and so on, which have been overprinted by one event or not? But we have another example on the mainland. Next, please. Which goes north from Doolin Point. Here on the left, you see the very nice rhythmic sequence of cross-running ridges in the main ridge. Here for about 500 meters. The distance is very similar from one to the other, about 20-22 meters. The elevation is 2 to 3 meters, and boulders incorporated may have a little bit less than 1 ton or around a ton, but more than 10 tons are also present. And the larger picture shows the southernmost 3 crossway ridges. So we have to find ideas how these have been formed. In the next image you see, next please. You see the distribution of these 2 unusual and new formations. The red arrows show the boulder tongues on mainland, the northern and the southern, and there is a double tongue more southerly. And on Inishmaan Island, there is a double one you haven't seen, but you have seen the 2 ones, one from the south, the other from north or west, from Inishmore western end. And the Crossway Ridge series can be found, or we have found clearly formed at 7 sites here in this bluish color, bluish signature. Next one. So finally, we come to conclusions in 2 steps. If we have a lot of field data from deposits, the kind, parameters, positions, and so on, we additionally need a bundle of data on their age and history, parallel to the history of sea level, and of course coastline position in relation to the deposits and the sea level, for conclusions on potential forces. That may be storm wave events or tsunamis. However, this all is not enough as long as we have not evaluated the relation of all these data to the environment, which give the framework like exposure, water depth, geology and petrography, pre-existing forms and sediments, climate and wave climate, including post-depositional weathering of boulders and bedrock, combined with the knowledge on intensities and dimensions of processes like dissolution or bioerosion. Only on this complex background, we should compare our local and regional results with those from other environments, other climates, and other timeframes to contribute to the state of the art in our branch of science. Next, please. This is not the end. And conclusion number 2, tsunamis as a relevant factor besides storm waves, of course, must be considered if deposits occur outside the strongest storm wave envelopes of the last centuries or modern times, as we have seen for the example of Inishmaan. Based on age of deposits at sea level during past events and other facts from a wider landscape, like tsunamigenic key features in fine sediment archives close to boulder sites, these irregular, non-sorted, or finding up sequences, for example. Investigations may be supported by field signatures of recent extreme events never recorded so far. For example, following the hurricane clusters along the Western European coastlines 2013 and 14, or the tropical cyclone Haiyan on the Philippines in 2013, described, for example, by Kennedy et al. In 2017. Both events left significant envelopes on deposits ranging to wider distance and elevation from the modern coastline. In the case of Galway and Arran, most of these higher deposits have been in place during a significant lower sea level, rising from about -5 meters from 6,000 to 5,000 pp on. And by the way, do we really need a superstorm category to avoid tsunami arguments? And what is a superstorm? How is it defined? Next, please. We have the keyword of tsunamis. West of Ireland, we find the Rockall Trough. It has a depth of 2,500 to 4,000 meters, and along its flanks are many submarine slides and the headscarves mapped by oceanographers during the last decade. Some of them are dated to the late Pleistocene and early Holocene. They represent the potentially nearest source area for tsunamis at the Irish west coast. Other sources for tsunamis, longer distances, are Eastern Canada and US continental slopes or the clusters of volcanoes in the Northeast Atlantic. Next, please. And final one. As a recommendation, the more extreme a marine event, the larger the area affected and the larger a study area should be. In the dispute on conclusions from fieldwork against theoretical approaches, nature's reality is the only standard of assessment to which all geoscientists should be committed. Thank you for your interest and your attention. Thank you.
Thank you, Dieter. That was a whirlwind of a field trip to
Aber zu lang.
Ireland and
Too
beyond.
long.
Well, it was an hour and I thoroughly enjoyed the, being embedded and placed in a landscape that is far from Australia. I really want to thank you for this really, depth and breadth of arguments that you presented today. And for our viewers, it will be uploaded on the Future Earth Coasts YouTube channel.
Okay.
And Dieter, for further arguments, you may briefly mention your email address for anybody to connect with you to further engage in a discussion.
Yeah. I will via your office, or?
If you just mention your email address now.
Yeah, okay. It is Dieter, D-I-E-T-E-R .Kelletat, K-E-L-L-E-T-A-T, Dieter Kelletat, slash, no, what is?
At
T minus online .de.
Yeah.
Yes. So Dieter Kelletat at T www.online.de.
Yeah, we will link your address also in the little
Yes, please.
of this video. So thank you, Dieter, for this tour around the world. We have visited many places in the Caribbean, in the Atlantic, in the Pacific Ocean. And I guess you made a strong argument for better combining field geomorphological results with theoretical modeling. And I hope from here on, we have a fruitful discussion with colleagues interested in combining these two scientific approaches to the problem of marine hazards.
Yeah.
Thank you. I stopped the recording. Yes, you would like to?
Yep. I think both is very important. The new digital modeling, calculation theories, and so on to test, but they have to have a base from which they are developed to solve an open question. And this base always must be the nature itself, or a fact from the nature itself. And that's why the old school field work is not gone.
No, I hear it.
It is still we need it still and need it to sample and to collect arguments which can be touched, which are not theoretical, which are nature's reality.
Yeah, they're the old saying, the past is the key to the future. Thank you,
Yeah.
Dieter. I stopped the recording. I stopped the recording now.